All right, so we'll get started. Today we'll be checking into the last chapter of the semester, chapter 15 on oscillations. So again, reminders, next homework is due on Tuesday next week, and then the last one is also up online, okay? Classroom disinfection today, Jeffrey and Luke, okay? All right, so in our daily life, there's a lot of motions that repeat itself, right? So for example, for guitar strings, if you plug it, then it will vibrate, comes back and forth, okay? So then anything or any motion that repeats itself at regular intervals, it's called periodical motion, okay? And that time that it repeats itself is called period. So that means it takes how much time to repeat a cycle. Frequency then is defined as the inverse of the period. So 1 divided by the period will give you the frequency. Okay, frequency that's in the unit of 1/second, which is also called hertz. Okay. All right. A very common type of periodical motion is called simple harmonic motion. So basically, you would have a mass attached to a spring. Then if you pull the mass to a certain point, you release it, and it will go back and forth. That's called simple harmonic motion. Okay. So the oscillation of a simple harmonic motion, you can call it SHM. Okay, for the abbreviation. Um, and the net force is proportional to the displacement and acts in the opposite direction of the displacement. We'll see about it later when we check the equations for displacement and velocity and acceleration, etc. Okay. All right. So let's take a look at the example of a simple harmonic motion. So if you have a mass attached to a spring, okay, you can imagine if you pull it to the one end and then let it go. Now, if there's no friction or friction is very small, you can see it go back and forth, right? So it goes in that direction and then push the spring, compress it to the amount which happens to be the same amount that you pull it. Okay, so the compression, if it's A, then or the when you pull it to A, then its compression will be also by A, but in the negative direction. Okay, so in that sense, then the force by the spring will pushing this guy forward. Okay, so you always go back and forth because the force from the spring. Okay, so you can see that net force here. So if you pull to one end, displacement is to the right, then force is to the left. Okay. On the other hand, if it's being pushed to the left, then force is to the right. Okay, so force is always opposite to the displacement. Okay, and acceleration has the same direction as the force, so then acceleration should also be in the opposite direction of the displacement. Okay, now typically this displacement, the maximum displacement, is called the amplitude. All right, so use symbol A. Okay, all right. Now, in any case, you'll see that net force will be equal to negative of k times x, which x will be the displacement. Okay, so then force and displacement, they are in opposite directions. Okay. In the lab, you can actually set it up so you can track the position of the mass attached to the spring like this. So you can have a roll of paper underneath it. And if you have a spark timer that can make trace on the paper, then the roll of paper, you can move it, make it move in a certain speed. So you'll see that this trace will appear on the paper. Okay. Again, you can see this figure to see where the full net force would be at a certain position. Okay, so over here, when the displacement is maximum, force is also maximum. Okay, at the middle equilibrium point here, the displacement will be 0, then the force will be also be 0. Okay. All right. So for the figure shown in the previous two slides, you can see the position of the mass. Okay, it looks like either sine or cosine function. So it actually doesn't matter if you use a sine or cosine function, because sine and cosine function, they are pretty much the same except a shift in the angle, right? So we will take a look on one example that you express the position in the cosine function. Okay, so that's assuming at the starting point, you pull it to a certain position over here. So when t equals to 0, x equal to a, okay, then you will have a cosine function. All right. If you use a sine function, then you probably start at when t equal to 0, x equal to 0, right? Because sine of 0 will be 0. So, but it doesn't matter. You can use cosine or sine. So different textbook will write this in different fashion. Some people prefer to use cosine. Some people prefer to use sine. So when you see that, just keep in mind they are pretty much the same. Okay, because sine and cosine are just a shift in position. So in here, the cosine function over here, so a will be the magnitude, okay, the maximum displacement, and then cosine, you can see cosine will have a range from -1 and 1, right? So then x wouldn't be greater than a or less than -a, so that's a region over there. In the parentheses here, it's 2 pi divided by t, which is period times the time t, small time t. Okay, so capital T is the constant, the period, 2 pi divided by that. 2 pi divided by that. So in one period, you can see the angle in the circular motion. This is 2 pi, right? So then this is angular frequency here. We call it angular frequency, but this is also the same thing when we will check in circular motion. That's the angular speed. Okay, so angular velocity. All right, so that's omega there. Now in reality, you don't always get a perfect cosine or sine function, meaning you don't always start from 0 or starting from the maximum, right? If you are starting from the maximum, then you have a cosine function. If you are starting from 0, you have a sine function. But in reality, you might be starting from any point, right? So then there's this we call phase shift over here in place inside the cosine function or inside the sine function if you use sine function, okay? So then you can, depending on where you are starting with, you can figure out what's this phi, okay? The phase shift. An example shows here, so cosine, that means when t equal to 0, you have maximum, right? Now, if you have a phase shift, so basically this would be the phi, okay? So that means when theta is equal to 0, then it's not at maximum, but it will be maximum when you shift by phi to the right, okay? So this is that guy, angle phi. All right. So then we can start with the expression of the general expression x as a function of time t. Let me see. Let me switch to this view over here. So I'm going to just write down the position as a function of time t because we are going to be referring to that. Okay. So x as a function of time t that equals to the magnitude cosine of omega t plus phi. So this is general expression. Okay. Then for the velocity of the mass, right? So you know that velocity should be equal to time derivative of the position, right? So then you are doing time derivative to this guy, okay? So then it will give you the minus right? The constant A, amplitude will be constant, so the A remains, okay? Then cosine of an expression over here, so then cosine becomes negative or sine, and then you're also doing derivative to the expression inside the parenthesis, right? With respect to t, so then omega comes out, so you have minus A times omega. So this omega comes from, you are doing time derivative to this expression, okay? And then sine of that guy. So then you can see velocity is equal to minus A omega, right? Times sine of omega t plus phi. So for sine function, again, it has a minimum of -1 and then the maximum of 1. So in that case, then your velocity should also have a maximum number, right? So velocity should have a maximum speed of A times omega, okay? Which is this guy. V max will be A times omega, okay? So then maximum velocity can be expressed in terms of the magnitude and the angular frequency as well, okay? So that's velocity for the simple harmonic motion. So for oscillation, then you do time derivative to the velocity function, right? So velocity, let me just pull this away for now. Velocity is in terms of this guy. So let's just keep A and omega here. Okay, so minus A omega sine. So you do in time derivative to this expression. A omega, they are constants, they remains. Then you are doing time derivative to sine of the function. So sine will become cosine, but there's a negative sign in front. So then minus A omega, right? Times cosine, and then you are doing derivative to the expression in the parentheses. So then another omega comes out. So it becomes minus A omega square, okay? So the oscillation then returns to the cosine expression, okay? So cosine function as the position, okay? So if your position is a function of cosine function, then your velocity will be a sine function, but then your oscillation will be, again, a cosine function, okay? All right, in this case, you can see, again, cosine has a minimum of -1 and maximum of 1. So then you can see oscillation should have a maximum magnitude of A times omega square, okay? We call that A max. So A max is equal to A times omega, okay? All right. So to summarize, position as a function of cosine, then velocity will be a function of sine with a maximum, okay, being A times omega. So V max will be A times omega. Position maximum will be the amplitude A, okay, and then oscillation maximum will be A times omega square, okay. So these are called the equation of motions for a simple harmonic motion, okay. All right. So pretty much you can see that once the position is given as a function of cosine, okay, so the parameters you need to know to determine the position is A and then omega, right? And then the phi. So then x varies as time t, the variable t, okay? And then once that's given, velocity can be determined, oscillation can be also determined, okay? All right. So this simple harmonic motion we look at was a mass attached to a spring, right? And then so from a mass attached to a spring, you can see that force should be equal to minus kx, all right? X will be the position. And force is equal to mass times oscillation, so mass times oscillation will be equal to minus kx, all right? So oscillation will be double derivative of the position with respect to t. So m double derivative of x dt squared equal to minus kx. Okay. Now if you move m to the other side, so then double derivative of x over dt squared equals to minus k over m times x. Okay, taking the expression for x as a cosine. All right. So then you'll be doing double derivative to a cosine omega t plus phi. So then the left-hand side equation will become minus a omega square, okay? Because you are doing double derivative. The first derivative gives you sine, and then one more derivative will give you back to cosine, okay? So cosine of that. But then you are doing derivative to the expression inside the cosine or sine function twice, so then it becomes minus a omega square, okay? On the left hand side, you can also plug in this expression over there. So it gives you minus km a times cosine. Okay. You can see then a and a will cancel out. Okay. And then cosine function and cosine function will cancel out. So then, oh, let's write it over here. So minus a omega square cosine omega t plus phi equals to minus k over m times a cosine of omega t plus phi. Okay, so a couple cancellations here. A and a cancel out, cosine and cosine cancel out. And then the minus becomes positive and positive. Okay, so you can see that omega squared equals to k divided by m. All right, where omega is the angular frequency, k is the force constant, and mass is the mass of the point mass. Okay, so you can see once you have the mass attached to a spring, then the frequency is pretty much fixed already, right? Given m and k, frequency will be determined. Our angular frequency is determined. Then frequency will be determined because angular frequency is equal to 2 pi over t, okay? If angular frequency can be determined, then period can be determined, and then frequency can be determined, okay? So in that sense, the angular frequency then equals to square root of k over m. You take square root here, okay, and here. And then period will simply will be 2 pi over, so from here you can see period will be equal to 2 pi over omega, okay. So then basically 2 pi over this will be period, okay. Then it becomes 2 pi times square root of m over k. Frequency then will be also determined. Frequency is 1 over capital T, all right? 1 over this guy will be 1 over 2 pi square root of k over m, okay? So once the spring is chosen and then the mass is chosen, then the frequency period will be determined, okay? All right, so let's take a look on the this first example here. It says a type of cuckoo clock keeps time by having a mass bouncing on a spring, usually something cute like a cherub in a chair. What force constant is needed to produce a period of 0.500 seconds for a 0.0150 kilogram mass? Okay, so it tells you the period, capital T, is 0.500. The mass is 0.0150. What will be the force constant or spring constant? Okay. You guys can check on the equation in the previous slides. So I think in the previous slide it says T equals to 2 pi square root of m over k. Okay, you are solving for k. All right, so we can take a look. So basically, you'll solve for k here, you rearrange terms, right? So t over 2 pi equals to square root of m over k, and then you square both sides, okay? So this is m over k then equals to t square over 4 pi square, okay? So then k will be equal to m divided by t square times 4 pi square, okay? Then you can put in the numbers here, 0.0150 kilograms times 4 pi squared divided by t squared, 0.5 second, okay? You should get k equals to roughly 2.37, okay, in newtons per meter, all right? And I see all your responses are about the same value, 2.37, okay? Good. All right, so we had the mass attached to a spring horizontally, okay? Now what happens if you have the mass attached to the spring vertically, okay? So pretty much everything else will be the same, okay? But you probably just change the reference point. So where from the natural position is for the spring, right? Now at this time, if you attach to a mass to it, then it will be equilibrium at some point here, okay? Delta y away from the natural springs length, okay? So after that, then if you take less as your new reference, then as your y equal to 0, then net force will be again equal to minus k times y, okay, with respect to that reference point, okay. Similar expression to net force equal to minus kx, okay. Then everything else should be the same, okay. So the reference point or the expression for the position, instead of writing x, you are writing y, okay. But you can use again y equals to a cosine omega t, etc. Okay. All right. So this is a similar here over here. Okay. So you take the new reference point where this equilibrium position to be y equal to 0, then your position now y versus time t will be a cosine function. Okay. Then time derivative of y will give you velocity. Okay, in y direction. That should be a sine function, but negative sign. And then for oscillation, it should be a negative cosine with magnitude. Okay, different magnitudes there. Okay, so let's take a look on this one. Again, a 0.500 kilogram mass suspended from a spring oscillates with a period of 1.50 second. How much mass must be added to the object to change the period to 2.00 second? Okay. You can use the same equation as the previous example because basically this is just changing from x direction to y direction, right? So you can use the same equation for the period t here, okay? And then the k is the same, so you are changing mass, so then period will be changed as well, okay? So go ahead and then give it a try. All right. So I think we can take a look here. So it tells you the first time 1.5 when the period is 1.5, right? Second. Its mass is 0.500 kilograms. So you can actually solve for K, right? From here. So basically divide both sides by 2.2 pi, 1.5 divided by 2 pi equals to square root of um 0.5 over K, right? Then you can square both sides and then you can solve for your K. Once you have your K, then you can calculate the new mass given so T2, this if we call this T1 M1. So T2 equals 2 pi square root of M2, right, over this K. Given this T2 as the 2 seconds equals 2 pi square root of M2 divided by that K you got from there. You can solve for M2, right? So you can do it that way, right? No problem with that. But you can actually do this in a different way, right? So because you are given T1 equals 2 pi square root of M1 over K, T2 equals to 2 pi square root of M2 then over K, right? So you have these two expressions. You can actually call this equation 1, this equation 2. You can do equation 1 divided by equation 2. That means the right hand side or left hand side of equation 1 over equation 2 on the left hand side should be equal to the right hand side of equation 1 divided by the right hand side of equation 2, right? So in this case, then you can see 2 pi and 2 pi will cancel out. This k and this k will cancel out. So you end up not have to calculate k, right? So then T1 over T2 is equal to square root of that. You can do T1 over T2 square. You can square both sides. Then that equals to M1 over M2. Okay. Now from this equation, you can solve for M2 directly. Okay. So M2 in this case would be equal to M1 times T2 over T1 squared, right? So 0.5 then times 2 over 1.5 second squared. Okay. That will give you your M2 directly, 0.889 kilograms, right? Now, how much more needed to be added? That means you are doing the difference of M2 minus M1, okay? So 0.889 minus 0.5 kilogram, that will be 0.389 kilogram, okay? Being added to the original mass, okay? So I see a couple of you guys had this one right, okay? All right, let me know if you have questions on this one. So if not, we can then check on energy in the simple harmonic motion, okay? So energy, by referring to energy, we are referring to mechanical energy, which means the potential energy plus the kinetic energy, okay? So total energy in the simple harmonic motion would be U. In this case, you have elastic potential energy because there's a spring, so 1/2 kx squared, okay? Plus 1/2 mv squared, okay? Now, if x is given as a cosine function, then v will be derivative of that. So then it will be a sine function with minus a omega in front of the sine, okay? Now you can take the expression for x and v, these two expressions into the energy equation over here. So then total energy will be 1/2 k x squared will be a squared cosine squared, right? And then 1/2 mv squared, v will be a squared omega squared sine squared. All right. Now remember, a couple of slides ago, when we say omega, we actually derive that omega is equal to square root of k over m, right? So then omega square, if you remember, let's go back a couple of slides here. Omega here is equal to square root of k over m. So then omega square will be k over m, right? That's what's being replaced over here. So omega is replaced by square root of k over m. All right. So now over here, you can see m and m will cancel out, right? So on the second term here, it becomes 1/2 k times a squared times sine of omega t plus phi in the parentheses, right? The first term is 1/2 ka squared cosine squared, right? So the 1/2 ka squared, you can single it out. Then you will do cosine squared plus sine squared, right? So cosine theta squared plus sine theta squared, that should equal to 1, right? So then the total energy in a simple harmonic just becomes 1/2 k a squared. Okay, k is the force constant times a will be the amplitude square. Okay, and if amplitude is given, then this is fixed, right? It's not changing. So the total energy in the simple harmonic doesn't change. Okay, total energy is constant. All right. If you plot it, you will see that the green top over here, the green line here is the total energy. It consists of two parts. The potential energy, right? The U in the blue curve here, and then the kinetic energy in the red. Okay, the two add up to be constant. All right. 1/2 k x squared. So x squared becomes this blue. V squared becomes that. Okay. All right. So the total energy is fixed. Then one pi is 1/2 mv squared. The other pi is 1/2 kx squared. And then total energy would be 1/2 ka squared, right? So then if you are given x, then you actually can solve for v, all right? Basically, 1/2 mv squared plus 1/2 kx squared equals to 1/2 ka squared, okay? Let me show you on the paper, maybe more clear here. So your total energy, or your 1/2 mv squared plus 1/2 kx squared, right? Kinetic energy plus potential energy, that's equal to the constant 1/2 k a squared, all right? Then if you are given x, you can solve for your v, because 1/2 can cancel out. So mv squared equals to then ka squared minus kx squared, right? So then to solve for v, you'll move m to the other side of the equation, right? I'll divide both sides by m. So then v squared equals to k over m a squared minus k over m x squared. So you can single out the k over m, okay? Then take square root. So v then equals to square root of k over m a squared minus x squared, okay? So which is this expression over here, right? Now if you do square root of that, it gives you absolute value, okay? Because v could be negative, okay? All right. Let's take a look on the third example today. So it says one type of BB gun uses a spring-driven plunger to blow the BB from its barrel. Calculate the force constant of its plunger's spring if you must compress it 0.150 meters to drive the plunger 0.05 kilogram plunger to a top speed of 20 meters per second. All right. What force must be exerted to compress the spring? So this one tells you you must compress a 2.150. So that's your amplitude. Okay. And the mass is the plunger's mass, 0.0500 kilogram. So you have A, you have mass. And then it says top speed. So that means V max, right? Top speed is 20.0 meters per second. So K, what's K? And then B, well, actually, yeah, B is looking for force. A is looking for force constant, B is looking for force. Okay. All right, so we can take a look here. So it tells us those three quantities, right? We also probably know that Vmax, you can look it up. Vmax is equal to amplitude times omega. Omega is the angular frequency, and the angular frequency is equal to square root of k over m. Okay, so then you can actually, by given Vmax and amplitude, you can solve for omega, right? Now once you have solved for omega, then you can solve for k because the mass is given. Okay, you can do it that way too. Okay, or you can use the energy we had. So 1/2 k a squared, that's the total energy, right? Total energy could be equal to 1/2 mv max square, right? When you have maximum speed, then your potential energy is 0. So then this is the maximum kinetic energy equal to maximum potential energy. 1/2 Ka square will be the maximum kinetic energy, right? So in lab A, you guys did this for a pendulum, but pretty much the same concept, except that in the pendulum, you have potential energy as gravitational potential energy. In this case, you would have elastic potential energy, okay? So you can set it up this way. And then you can solve for your K from here. I think that's the most convenient way to do it. It turns out will be the same expression if you go through those, right? So then in that case, omega is equal to, from here, omega is equal to V max over A, right? Then you set up that omega equal to this guy, so equal to square root of K over M. You do square on that side, squared on that side. Okay, so V max square over A square equals to K over M, right? So that tells you your K is equal to MV max square over A square, right? From here, you will also arrive that K is equal to MV max square divided by A square, right? Because you divide both sides by A square to give you K. So they are the same expression, really, okay? So you then just plug in the numbers here. So 0.05 kilogram times the maximum 20.0 meters per second square divided by the maximum amplitude 0.150 meters squared. Okay, that will give you roughly 889 newtons per meter for the spring constant. All right. Now, once you have that spring constant, you can solve for the force needed. So that force should be equal to K times A, right? You need to compress it to a maximum. So then 889 newtons per meter multiply 0.150 meters, that would roughly be 133 newtons, okay? For the force needed to compress the spring, okay? And yeah, so most of you guys got the right spring constant, and then everyone actually got the right spring constant. And also, most of you guys got right on the force needed. Okay. All right. Okay. So now let's again take a look on the energy curve here. So you have the potential energy, you have the kinetic energy. Okay. Now take a look at the potential energy over here. Okay, so if you are at the equilibrium position, then your potential energy is 0, right? And you can realize that when we talk about the stability, so at the equilibrium point here, if you move your object slightly to the left or to the right, right? So you can see then if you move to the left, then the force will be to the right, right? Because force is opposite to the direction of the displacement. And then if you pull to the right, the force will be to the left, okay? Now, the force could be also be calculated with derivative of the potential energy with the position, okay? It will be negative of derivative of U over dx. So in this case, you can see if you are doing derivative of u over x, that means you are looking for the slope on this side. So on this side, the slope will be negative, right? Negative, and then with the negative sign, you'll see the force will be positive to the right, okay? On this side, the slope at any point will be positive, and then with the negative sign, that means the force when you are on this side will be to the left, okay? So you can see either side, on either side, if you displace your object to slightly off the equilibrium position, then it will be pulled back to the equilibrium position, okay? So then that gives you the stable equilibrium point, okay? So stable equilibrium point, that means when you are doing the derivative or minus du over dx, you will have, you can see at this point, you have your slope equal to 0, okay? So if minus du over dx is 0, then that's your stable equilibrium point, okay? Now, a couple other scenarios, if this is the case, okay, so then this is a not stable equilibrium position, okay. Although, if you look at du over dx is still 0, but it's not, okay. So this is not a stable. So in that sense, minus du over dx doesn't necessarily tell you if it's going to be a stable or not stable equilibrium point, okay. It's just going to be an equilibrium point, but you cannot tell. Also on this one, it's not a stable one, okay? All right. Yep, I think that, so similar here, okay, you can see it's going to be stable over here. Now, on this side, okay, it's stable on this side, but not stable on that side. If you displace it towards that side, then it will roll off, okay? Okay, I think that will be it for today, okay? We'll stop here, okay?